Everything that is coming to you as the input will be, let's say, standardized mean and variance. Do people understand this? Is anybody having any questions about what I just said? If this is people keep saying batch norm is important. This is basically what it does. It's because you're trying to figure out for the intermediate layer, just before the intermediate layer, trying to figure out, so you have an intermediate layer here of nodes, right? And then they have weights coming, they have inputs coming from the layer before it, and they have these activations for these inputs. And you want to essentially make sure that they are well behaved. They're always within the same sort of a range. And the right way to do it is to work on the entire network before, such that everybody works just so in tandem that these values here will always be zero mean and some required variance. That's impossible to do because there could be about 1 million weights before you. They're all changing at the same time. You see this? So the wrong way to do it is what we'll try, because the right way doesn't work. Okay? What we'll say is, to heck with it, we'll forget about the inputs, forget about how these guys wound up having the values they had. I'll take the activation values at this particular point of time for any particular mini batch that I'm passing through, normalize them to have zero mean unit variance. Do you see what I'm saying? Okay, so I'm basically just going to forget about, these guys wound up having some values based on the weights and the thresholds of the previous layers, etc. These guys had some activations. I'll just basically take those numbers, forcefully convert them into z-scores, essentially. You see what I'm saying? If I do this, I'm guaranteed that my inputs will be well behaved. But it turns out we're going a little too far. An idea is that it is possible that while just as in the case of Xavier initialization, you notice that we wound up putting the weights to have a different variance, zero mean but 1 over n variance, where n is the fan-in parameter. So different layers might wind up having different mean and variance. What you really need to do is, I don't care about your parents, but I'm going to start, say, from now onwards you shall have variance beta, and the mean beta and variance gamma. That's what I want to say. Okay? How can I do this? I do the first step, then I got z-scores, which are zero mean unit variance. And then I won't pass the z-scores to the next level. Instead I pass gamma times z plus beta. If z is zero mean, what do you think is the average of this expression? It's just beta. And the variance would be gamma. Right? This is what I want to do. All I need is some rich uncle to tell me what's beta and gamma. Okay, just 1 second. If I do this, then everything seems kind of okay. I mean, look, the real right thing to do is make the entire network behave just so that by this layer, things are already scaled. But who are we kidding? That's too hard. Okay? The very easy thing to do is to just, at every level, convert the activations into zero mean unit variance. That's a little going too far in terms of simplifying the problem. Instead, you'll say, you guys can have different means and variances. Gamma being the variance and beta being the mean. Do you see what I'm saying? And then these inputs are then fed into the next layer. And then the neural network moves on. The only question is, who gives me gamma and beta? First idea might be that, oh, I'll just figure out, I'll randomly generate some gammas and betas and throw them in. The beauty of batch norm idea is your rich uncle is this really slow rich uncle, gradient descent. Okay? The crazy thing about modern neural networks is let the gradient descent do it. That's it. So you will let the gradient descent figure out both gamma and beta. This is kind of mind-bending. Right? Because you originally thought gradient descent is only going to look at the weights. Now you're saying it's not only looking at the weights, it will also try to learn how to normalize itself at the various, how the network should normalize itself at the various layers. Just so. Just so what? Just so what? What does gradient descent do? What does it optimize in the end? Just so that the loss function is minimized. That's it. It will find gammas and betas for each of your layers. Each of your layers it will find gammas and betas, different betas and different gammas. Because these will become weights. Just like you're learning weights, you're learning gammas and betas too. You will start by setting them some values and then they will slowly change. And it's the same blind gradient descent. Now, this is why it's very important to understand. Remember what I said, a neural network is a big function of composed functions, because of which the backpropagation is automated. Step by step by step, right? You agreed with that. Have I changed that point? Is now the neural network not a composition of functions? It still is. Because after you took the linear sum of weights, then you took the threshold function on those values, then you did this transformation on a bunch of those values, where gamma and beta are parameters to be learned. And you will just learn the partial derivative with respect to gamma, partial derivative with respect to beta, and use them to change gamma and beta and lead in the right direction. Again, if anybody thinks they completely understand how this stuff is going on, yeah, you're hoping that gradient descent will do the right thing. Okay, but really these are little changes for more and more parameters. And the trick winds up being, if I have a problem, how do I convert it into a problem that my rich uncle will do? Which is really slow rich uncle gradient descent. There was a question before. Yes?
So when we say that we don't necessarily want the intermediate layers to go to zero in one variance, why do we not exactly want them to?
Because it turns out that if you do that, again, there are much of what is going on right now is engineering. There's actually a beautiful, so 2 years back in 2017 at NeurIPS, Ali Rahimi and Ben Recht, these two authors, were given a prize, 10-year Best Paper Award prize for the work that they did 10 years back in NeurIPS, that was published in NeurIPS. Okay? And so then they get to give a 10-minute presentation about it. And I highly recommend that you watch Ali Rahimi's NeurIPS presentation. Basically, he starts by saying, like one of your crotchety old granddads saying, you guys, you don't have any theory. Which is true. Batch norm has become the bedrock of the modern deep learning. We don't completely understand why it works. Little by little we may be understanding, but not anywhere close to. So the answer to you, the simple answer is, it works better if you put gamma and beta. If you don't, it doesn't work as well. Okay? And then now that you figured this out, then you will make up new ideas. Saying it turns out that actually just as, you could have asked, the interesting question is, why didn't you ask that same question here? Why did I do the weight normalization such that the variance is the same thing? There is no real reason when I normalize things, they should always have unit variance. Okay? Again, batch-num is so huge in terms of engineering that what used to take, I forgot the number, the first time in the 2015 paper by Jagadi, Christine Jagadi and somebody else came out, they basically said, what used to take weeks now takes hours to train. Because the number of epochs that you need to get the weights to some reasonable place has reduced quite significantly. Which is why you start off, if your interview is going not all that good, you should say, I'll then use batch-num. And then you'll say, what is the batch-num? Because they know most people don't understand. Then you throw this stuff up. Mug it up tonight, just throw this up, and get it done. Okay? Okay, so that's about batch-num. So that's our first, again, the mind-bending thing is gamma and beta are learned by backpropagation. The same old vehicle which was learning the weights is also learning this. Okay? Now we get to this other part, which is actually learning in general. Of course, what we're trying to do is we got into some input and we're trying to figure out basically different network configurations. Even if you have a fully dense network, if you make if the network winds up learning some of those weights to be zero, in some sense it's learning a smaller network. Okay, so this network is basically giving you a family of functions. And you are kind of learning like any function from there that minimizes the training error to zero. A training error, and maybe to close to zero. Okay, so in general, this kind of brings us to this question in machine learning. Each network configuration, that means each of the weights for this network, that can be thought of as a hypothesis. It's basically your hypothesis about what the function is that is underlying the input data. Right? Many functions might actually be consistent with the input data. We have seen this. If I give you 4 numbers, I remember the time when I said 2, 4, 6, 8, and you guys said 10, and I said, that's not true, it's 42. Okay? Because there are like a million functions that I can fit such that they will be 2, 4, 6, 8 at the first x1, x equal to 1, 2, 3, 4. And yet take any random other value afterwards. And the entire point of machine learning is not fitting to the data that you have in front of you, but correctly predicting the data that you haven't even seen. To do this, you need to have some metaphysical biases about how the world works. Because all of these functions are just equally good in terms of capturing the training error. So why are you picking one over the other? Do you see what I'm saying? So much of machine learning is to realize that not all hypotheses are created equal. Of all the zero error hypotheses, you might like some better than the other. If you use knowledge other than the training data to figure out which hypothesis to pick, that's external knowledge from outside of the input data, right? You can think of this essentially in machine learning terms, you call this bias. I understand outside of this room, if I say bias, people will say, what a bozo, you should not be biased. But then you should say, if I'm not biased, you won't get any learning done. We are all biased. Okay, because, and remember, can anybody remember a good example of bias that I gave here in this class about how people use bias?
Tigers and tigers.
Yeah, no, the other one. I give lots of examples. Yes? No, I'm talking much simpler one. Remember the kid? You took the kid and said, son, this is a bus. Right? Why did the son think the entire damn thing is a bus? Why didn't this kid say, maybe the driver is the bus? Maybe the steering wheel is the bus. Notice that kids don't know these words. They don't know their words and their meanings. They're trying to learn the words and their meanings at the same time. Why did the kid basically say, any of these things can be bus? So a Bayesian kid will say, anything that can be seen around here could be considered a bus. I'll remember this. And most Bayesian kids are under the bus. Right? But it's important to understand that the right way to do machine learning is to be Bayesian. In fact, when we get to probabilistic reasoning, and when we talk about statistical learning foundations, we'll say that the real foundations of machine learning are Bayesian learning, where you never make up your mind. You say, before I saw the data, I had a prior over which hypotheses are more likely, which are less likely. After seeing that data, I have a posterior about the likelihood of the different hypotheses. I won't pick one. I'll keep all of them to predict any test data you give me. And basically, I take the weighted prediction. Committee vote. If you do that, it turns out Bayesian learning is the right way to do learning. Much of the stuff that we talk about as the problems, such as overfitting, is because we are not good enough to do Bayesian learning fast. We, the humans, certainly are not. Our machines are also not able to right now do Bayesian learning efficiently. The theory is there, but in practice they're extremely slow. So just like the Bayesian kid who went under the bus, your Bayesian computer also basically won't go anywhere because it's keeping all the hypotheses around. But once you know what is the right thing to do, it actually winds up helping. And in fact, many of the things that we'll talk about here, you can see them as trying to get to Bayesian learning without doing it. What else did we do, by the way, where we tried to get to the right idea, but with different ways? The entire gradient descent should really be done using Newton-Raphson method. Newton-Raphson method would require you to use second derivatives. Second derivatives means Hessian. Hessian means m square numbers. So instead, much of the so-called first order optimization methods, such as the momentum method and the Adam and all these things, are not doing Newton-Raphson, but somehow getting an efficiency which is between just pure gradient descent and Newton-Raphson. The same thing can be thought of for the entire machine learning. Much of machine learning's problems like regularization and randomization that we'll talk about, which is connected to dropout, which you wanted to hear about. They're all essentially because we are not good enough to do Bayesian learning, but we know that we should have done Bayesian learning, so every once in a while we'll do some fixes to our algorithms. It's a very useful thing to remember because it's not what the idea is, it is where the ideas come from. That's important in life. I understand as far as this exam for this question is, this particular course is concerned, you just want to know what the idea is so that you can plug and check. But after this, the way you will ever use any of this stuff is where do ideas come from? As against just being downstream from the place where somebody else is producing the ideas. Okay. Now, so from Bayesian perspective, there is a non-uniform prior or hypothesis, etc. In general, a bias basically is sort of making you pick one of these hypotheses over the other hypothesis. Instead of just keeping all of them, this is what Bayesians will do. Normally, bias basically, for supervised learners, in general, typically it comes from the background knowledge, which either you have learned over your period of your life, or you came into this world inbuilt. So for example, the kid bus example, that's what's called whole object bias. Kids just seem to come into this world having this bias. They'll assume, until proven otherwise, if you sort of show like this and say the class, I'm not saying the red guy is the class. I said the whole thing is the class. Okay, that allows for learning actually to take place more efficiently. Okay, so for supervised learners which don't have any background knowledge, then such as neural networks, you need to smuggle background knowledge in some strange ways. Okay? And the strange ways include, for example, so basically you need to make them prefer specific classes or functions or to keep more functions around. To reduce the problems involved in overfitting. Okay? The three ideas that we'll talk about today would be, one is the simple regularization, which is basically what is called the loss function engineering, where I already kind of explained to you that in addition to that, the error over the training data, you add some factor that tries to do something to the functions farm itself. For neural networks, the functions farm is just the weights, and you try to minimize the norm of the weight vector. That's regularization. Okay? Most networks do this. So when they just say loss, they'll say we're reducing the training data plus a whole bunch of things that we have in our bag, we throw them in. And this is all added to the loss. And then the advantage is that everything, once you tell your the network specifier, the loss function, it knows how to automatically do the back propagation because it composes them from little pieces. That's why it was very important to understand that you could actually get the gradient for the sigmoid function by just looking at pieces on a data. That's what gives you the confidence that this is actually doable. Love is not just making it, right? Okay, the one is regularization. The other idea is actually randomization during learning, which essentially says, hey, I'll just keep around all the hypotheses. Typically, keeping around all the hypotheses in the right way is extremely costly. So you kind of do it a little more efficiently. That's the idea of dropout. So dropout is basically trying to do Bayesian learning over neural networks. Okay, and if we wind up doing decision trees, we will also talk about this idea called random forests, which is another idea that's extremely useful. And random forest is again trying to do Bayesian learning with decision trees. Not just keep one decision tree, have a whole bunch of decision trees. And let them all vote on every new example. And take the committee vote. If you do that, overfitting is not a problem. You see what I'm saying? You heard dropout and you thought, some of you probably heard dropout and they thought, oh, this is something that's only true for neural networks. It is just an idea that is connected to fundamentals of machine learning. And a particular version of it as applied in neural networks has been heard. Okay, but I can show you what dropout is in the next slide, but the important thing is to understand why do you need dropout? Which is because really, if somebody, who is this guy? I can think of this, the baseball guy who said, when you come to the fork, take it. Okay, that's what Bayesians do. When most of us come to a fork in the road, we'll either take the left or the right. Bayesians say, let's take the fork. Okay, which means keep all the hypotheses with their likelihoods. It's extremely hard. We don't do that well. In fact, humans basically jump to conclusions all the time. But that's why we are bad learners. Okay? But it turns out that you can do that. If you do the Bayesian learning versions, then you reduce the overfitting. Okay, so change in the loss function, as I already mentioned, you wind up basically one idea. There are many, many different ideas for regularization. One idea is loss is equal to error on training data plus alpha times the norm of the weight vector. Alpha is a true hyperparameter. It's not, gradient descent is not giving it to you, you just set it up yourself. And you are minimizing this whole thing. You see what I'm saying? And you have to understand that don't make any specific feature have too high a weight. That's approximately what you're doing. By minimizing the norm of the vector, you're ensuring that features don't start specializing on single data points. That way lies perdition. That way lies memorizing the data rather than learning the patterns in the data. Okay? So that's the That's the basic idea of regularization. There are other kinds of loss function engineerings can be done. In fact, if I have time, I'll point out to you that remember in the extended part of the last class, I said adversarial examples, make a city bus that looks like a city bus to all of you, but is 100% an ostrich for your network. And these, and I was actually having a conversation with other people after the class, adversarial examples don't just happen by happenstance. Somebody designs them. And I was giving this example again, my Star Wars example. Things like TIE fighters don't just randomly come and hit into the only vulnerable part of the Death Star. You need Harrison Ford and his deliberation for the first 3 hours of the movie to do that. Adversarial example means somebody else with intelligence are trying to catch you. So these adversarial examples are made. And you know how to make them? So I'll just tell you, because I brought it up, I'll mention it to you, that here's the way they'll be made. You have taken some network, let's say that's being used for image recognition. And then you put the school bus picture to its inputs, and it's a school bus. But you want to say, hit on its head and say ostrich, say ostrich, say ostrich, say ostrich. But you should do this without changing the weights. The weights are already there. Weights have been learned during the training. Instead, what you are saying is, remember in the normal training, input is constant, weights are the variables. How many of you remember implicit differentiation from the old days? So if the input applied to the function gives the output, you can either consider the weights to be the variables or the pixel intensities to be the variables. So imagine I keep the weights the same, I start fiddling with the pixel intensities until the network basically agrees with me that this is an ostrich. That's how adversarial examples are made. The only problem is you can fiddle with the pixels so much that it actually is an ostrich to everybody. In which case it's not an adversarial example. You understand what I'm saying? So what you need to do is when you are fiddling, so the original image is a vector. The fiddled image is a new vector. You take the difference. You want to minimize the norm of the difference image. If you do that, nobody else can tell that this is not a school bus. So everybody else thinks this looks like a school bus. So that picture that I showed you in last class, it was sort of shown as if there was nothing going on. This noise, it was Harrison Ford noise. It was carefully constructed. To your eyes, it looks like noise. To your eyes, everything looks like noise. This was very carefully constructed deltas added to this image, which will give you this image, which looks exactly like a school bus. And it's high certainty an ostrich for your network. Now the question is, how did you compute this? Basically, you had to learn how to change the pixel intensities. You have one old rich uncle, gradient descent. Use the gradient descent to learn to change the pixel values. And you make sure that the two images are still looking like school buses to everybody else by adding a loss function on top of this, on top of just agreeing with me that this should be an ostrich. You will also ensure that the loss function takes into account the difference in the images and minimizes that difference. This should be properly bending your mind even more. right? Because we said gradient descent 3 classes back, we started doing little by little expressions of chain rule, which itself is actually far away in abstraction from fx plus h minus fx by h tends to 0. On top of it, we built multi-layer networks. On top of it, we said to heck with all of this, we just use computer science and just automate the composed functions gradient computation. The moment we did that, now we don't have to worry about what we are adding to the last function, because it will get taken care of. And I don't need to worry about where these parameters like gamma and beta in the batch norm are coming from, because they too will be learned. Okay? Fine. So, let's see, where are we? Okay. So other kinds of loss engineering is possible too. An example is adversarial example that I just showed you. Okay. The other one is just do Bayesian learning already. Okay, be Bayesian. Okay? Maybe not fully Bayesian, sort of a little more Bayesian than what have you been doing, what you've been doing. Okay? And so idea is keep more of the hypothesis around. An idea would then be to say, instead of learning a single network, let's say you learn an exponential number of networks at the same time on the data. They all predict the data. They all do reasonably well on the test data. They all try to minimize their test error, training error. But they are learned at different times. And so basically they are learned on different, let's say, parts of the inputs. That means if you have, let's say, 10 billion examples, you could, for example, use some of the examples to just train one network, some of the other examples to train the other network. That's an important, a rudimentary idea. Then you have 2 networks, and then you can make them be a committee. This is the way you will wind up getting Bayesianism. Dropout does this. And Dropout does this in a very clever way. What it does is it has the network. Let's say this is a network that I have. Every time, basically, when gradient descent is happening, you will have to update some weights, all the weights. In general, you update all the weights. Right? That's how gradient descent happens. What Dropout says is at every epoch, you randomly act as if some of these weights don't exist. Those connections don't exist. So it becomes like this, randomly. Every epoch, you pick a random network by just basically saying, you toss a coin to decide whether or not this connection exists. If the coin says, yes, the connection exists, you will keep the connection. If it says no, oh, you don't exist. If you don't exist, I don't have to update you. If I didn't update you, that means I didn't learn your value on this part of the samples. Did you get this? Strange nonsense. Right? Right?